Hello, welcome to the webinar, The Language of Concurrency. This is an introductory webinar, so you don't really have to have a lot of prerequisites, although some understanding of threads and locks will help. So we'll be talking about things like threads, Dataraces, message passing, sequential consistency, and the general plan of the webinar is to first of all carve out the whole area of concurrency using sort of binary divisions. So first we'll just talk about what's the difference between processes and threads. Then another subdivision is what's the difference between multiprocessing, multi-threading, and parallelization. Then we'll talk about what's the difference between shared memory and message passing. Then I'll talk about the problems with that you will encounter when writing concurrent programs, and these are roughly Dataraces and Atomicity violations. Then I'll talk a little bit about the relaxed memory models. This is something of a new topic in recent years that first came through multiprocessors with relaxed memory models. The next topic is more theoretical, but don't get intimidated. Sequential consistency is actually something that's pretty easy to understand, and the DRF guarantee, which I will define, is something that actually lets us write concurrent programs and understand them. Then I will summarize all these risks of concurrency and finally tell you how to deal, how to minimize them, how to debug, and how to test your concurrent programs. So that's the plan. Let's start with the major subdivision between sequential programming and concurrent programming. We all know how to do sequential programming, right? Because we've been writing sequential programs forever. And let me just stress these two points that actually differ between sequential and concurrent execution. In sequential execution, one action follows another. That's a very pretty simple statement, right? And what's even more important is that the effects of previous action are visible to the next action. Also, pretty simple and almost trivial statement. And both these statements are violated in concurrent execution. And look at the background of this slide, and you'll see an illustration. This is three threads executing the same program in this case, the same code, and they are executing it concurrently. So they are sort of executing one on top of the other. Some statements are executed at the same time, some of them are interleaved, and there is no specific execution of some of the parts of the program, right? And this execution changes from one run of the program to another. Every time you run a program, there's a slightly different interleaving of your threads. And another thing is that at least conceptually, and when you are running on a multiprocessor, that actually happens, that multiple actions can happen at the same time. This is where you see these lines of code overlapping each other. They actually happen at the same time. One is running on one core and the other is running on another core. And of course the problem is, what if they are both accessing the same memory? Like here in the case, node next equals TMP is repeated twice, and the TMP could be different in both. So which write will go through? Which one will be overwritten? And the third problem is effects of actions are not, it's not obvious how they are visible to other threads. Are they visible immediately? What does it mean immediately? Are they all visible in the same order? Or some threads might see writes in a different order than another? And all these problems are actually addressed by the so-called memory model. Now let's talk about memory sharing. This is a very important distinction, and in terms of programs, the distinction is between processes and threads. So a process usually corresponds to like an application, but some applications have multiple processes running. It's just every process has its own address space, and the operating system makes sure that they cannot read each other's address spaces. So a pointer in one process is, even if it's the same value, it doesn't access the same memory as in another process. So if processes want to communicate with each other, they have to use special communication channels. They usually exchange messages, or they can talk through sockets. They can use files to share information, or they can use memory mapped files. And in some cases they can even request from the operating system a piece of shared memory. With threads it's easier, because threads share the same address space. They are within the same process. So they can write and read from the same memory address, and they see the same data. Some data is more shareable than others. For instance, by convention, stack variables, your local variables within your function, are not supposed to be shared. But this is not a very strict requirement, and it's possible to share them. And sometimes it's a good thing. In many cases, it's a bad thing. Because when you are sharing your local variables, when your function exits, all these local variables disappear, right? And if another thread has access to them, it will see the disappeared variables, and that can only be trouble. Now, this is possible in modern languages like C++ 11 that have lambdas, and you know that lambdas can actually capture local variables. And if they capture a local variable, then this variable becomes, and you run a thread that's running this lambda, you know, suddenly your local variable is shared. These lambdas that capture variables are called closures. That's why I wrote here, beware of closures. Closures introduce sharing into your threads. Now, the thing about memory sharing is that when threads are concurrently accessing the same memory locations, they can collide with each other. They step on each other's toes. And if you don't do something special, which is called synchronization, then you'll be in trouble. And I'll talk about it. Now, from the practical point of view, when should you choose processes and when should you choose threads? Processes are heavyweight. Creating a process takes a lot of resources, and it takes time. So if you are doing heavyweight concurrency, that's okay to use processes. If you don't create lots of them, and if you don't have to dynamically create, destroy these processes, then you're fine. And also, communication between processes is rather expensive. So they are best used for calculations that require a lot of work and little communication. With threads, it's the opposite. Threads can be created quickly, reasonably quickly, on demand, and they can easily communicate with each other, although you have to be careful to avoid these problems of concurrent memory access. Threads versus tasks. This is a distinction that came into concurrency or the mainstream programming rather recently with the advent of multi-cores. And these two areas, multi-threading and parallelization, are pretty distinct, although they are based on the same mechanisms. So multi-threading is when you are creating threads explicitly and you assign some work to them. You say this thread will execute function F, which is called a thread function, or sometimes thread loop, because they often loop waiting for assignments. And this kind of programming is very good to improve latency. And in fact, multi-threading has been used for a long time on single processor machines, where they actually don't speed up your program. Your program doesn't run any faster, but it has better latency. It responds to external events or to GUI events faster. The problem with having threads and managing them explicitly is that it's a programming paradigm that doesn't scale very well with the number of cores, because the number of threads that you are using in your program depends on the demands of your program, and usually is either hard-coded in your program or based on some external demands. It doesn't depend really on how much resources how much computing power is offered by your machine. And parallelization is something that steps into that area. How to improve the performance of your program, how to process more data per second, and how to take better advantage of the multiple cores that you have on your machine. And the more cores you have, the faster your program should run. So in order to achieve this, you parallelize your program, which is different from creating threads, because you want to divide your work into smaller units that can be parallelized, and these are usually called tasks. So your program creates lots of tasks, and the system decides which of these tasks will be run on which core. So you are only giving a hint to the system, telling it, you know, these tasks can in principle be run in parallel. I'm not forcing you to run them in parallel, right? But if you think you can get a better performance out of it, please run them separately. You can create, let's say 800 tasks, and if you run on an 8-core machine, you will execute, let's say, 100 tasks per core. So on a particular core, you will have 100 tasks executing one after another sequentially, right? But you have 8 cores that will be running in parallel. So theoretically, this improves the throughput, the performance. In practice, it's a difficult problem. Okay, not all programs are easily parallelizable, so it's not always that simple. But the principle is that the parallel programs will scale better with the number of cores. So again, how do you choose between these two? And it's mostly a trade-off between latency and throughput. If you really care about throughput, then you use parallelization. If your main concern is latency, then you create your own threads. How do threads communicate? Here's another division, two big schools of concurrency that are often fighting each other and discussing in every single concurrency forum. You will see people who are for memory sharing and for message passing. They often dislike each other. So shared memory is between threads. You can share the same memory. You have access to the same memory. So why not use it, right? The problem is that it's dangerous. It requires precise synchronization. If you don't synchronize accesses, then you will get things like dataraces, atomicity violations. And then if you synchronize too much, you have too many locks, then it leads to deadlocks, live locks, and stuff like this. Synchronization is usually done, in most cases, is done through locks or critical sections. They're all the same, really. And at the lower level, people also use atomic variables, or in Java, it's called volatile variables. But that's the area of lock-free programming, which I do not recommend easily. Okay, the other school is message passing. Don't share memory. So even if you are within the same process and running threads, your threads should not access shared memory. So this is sort of a discipline-based programming where you promise, I will not share memory between my threads. I will only use message passing. I will pass messages using message queues, channels, mailboxes, and stuff like this. All these mechanisms are essentially use message passing underneath. Now, the good thing about message passing is, and many people will tell you that, it scales very well to distributed environments. Because although the implementation of message passing between threads, for instance, is very different than between machines on a network, the interface could be the same. And the interface, usually the low-level interface is, give me a buffer and the size of the buffer, and I'll pass it to another computer or another thread. And of course then, both sides of this channel have to agree on how the data is encoded in the buffer. I mean, if it's an int, then it's fine, or a bool, right? But if it's an object, you have to serialize the object, and then on the other side, you have to deserialize this object, and so on. And if you have heterogeneous machines, one of them has a different endianness, different byte order, and different sizes of integers. All this have to be encoded properly into the buffer. That's called marshalling the data. So even though it's more general, it's actually slower, especially if you try to use exactly the same mechanisms in distributed environments and within a process where usually you don't need really that much marshalling, and all you need is serialization. So if you only use message passing between threads, then you might have some shortcuts, maybe, like you might be passing references in your messages, and of course then you introduce sharing through the backdoor, and if it's unintended sharing, then you have all these problems that you have with shared memory. Now I would recommend using both. In fact, I mean, a lot of stuff can be done with message passing, and it's kind of safer than using shared memory. But when you are dealing with lots of shared data, lots of exchanges, then probably shared memory is more efficient. And often a hybrid approach is the best, in which, for instance, you modify some shared data and then you send a message to another thread saying, hey, I have modified it, look at it now, and so on. So there are many possibilities here. It's not just black and white. So let's talk about these races, the horrible races. So let me define what a data race is. And in order to understand a data race, let's first talk about the conflict. That's a simpler idea. Conflict is when two or more threads are accessing the same memory location, and at least one of them is writing. Okay, that's called a conflict. Now, not all conflicts are bad. The bad ones are called data races. And actually some people say not all data races are bad, but I don't believe that. So a data race is a conflict with no intervening synchronization. So if you don't provide for any kind of synchronization between these accesses, then you have a data race. In most cases, the synchronization is done by locking, or in Java, there is a keyword synchronized. And the important thing is to be locking both reads and writes with the same lock. If you remember that, you will have much fewer problems. But there is another low-level way of synchronizing things. In C++, it's called atomic variables. In Java, it's called volatile. And that's called lock-free programming. And that should be really left to gurus of lock-free programming, because it's extremely easy to make a mistake. And here's an example of code. This is the first code example in this webinar. Two threads are executing. One thread is setting a shared variable ready to true. And the other thread is reading this variable ready and checking if it's true or false. So if ready, then do something. Okay? So let's look at our definition of a conflict. Is this a conflict? Yes. One thread is writing, another thread is reading the same variable. So that's definitely a conflict. Is this a bad conflict? Is it a data race? Yes. At least in this code, you don't see any synchronization, right? The writing to the modification of ready is not under a lock, and the reading of ready is not under the lock. So this is a data race. And you might say, so what? Right? But unfortunately, a data race is a bug, and it's really not that easy to figure out why this is a bug. You just have to trust that data races are bad. Okay, and I will try to convince you if I can. But before that, I'll show you another problem. It's data races is like when you are dealing with one variable and just one access per thread. Atomicity violations are a little bit more complex because they either involve multiple locations or the same locations but multiple modifications. Okay, so they are sort of a higher order problems. And here's another code example. So we have this method addLink that adds a new link to a linked list. So this is a singly linked list. Okay, so to add a link, it creates a new node, and for this node, it sets the next pointer to the current head. Whatever head is pointing at, it will become the next, right? And the second operation is switching head to point to our node. So our node will go between the head, will become the head, right? And now this code will execute in 2 threads at the same time. And look at the picture on the right. So one thread creates N1, the new node, and another thread creates N2, another node. And they do it sort of at the same time. And then both of them start executing set next on this node. Okay, fine. So the first node did set next on N1, pointing to N, which is what head is pointing to. That was the first element in our list. And at the same time, the second thread, it's pointing its N2 to the same N. Okay? So far, it's still working, but we can see the problem, right? And then both threads execute the next instruction, which is head equals node. So depending on which one gets there first, and this is why these things are called races, because they are now racing. And in fact, the one that gets there first loses. In this picture below, you see the thread that owns N2 set head to point to N2. And then the thread that owns N1 did the same, but set head to N1. So now the thread that owned N2 finds itself in a sorry position when its addition actually is no longer in the list. It was kicked out by the other thread. So this is called atomicity violation, this kind of problem. And it's easily fixed if you do both operations, both the set next and head equals node, under the same lock. Right? One of these operations, notice, one of these operations is a read, because we are reading head, and the other is a write. We are writing into head. So, locking will solve this problem. But if you don't lock, then you have a bug in your program, and your data structure gets corrupted. Okay, so now let me explain why data races are so bad, and the best way to see it is if you consider relaxed memory models. And this is a problem that can be seen both from the perspective of processors and from the perspective of languages or compilers. So let me start with processors. So if you have a multiprocessor or a multi-core, the simple approach would be to say, okay, every processor, if they want to access memory, they have to access main memory, right? And that's fine, except that accessing main memory takes a long time. It takes like on the order of 100 cycles. So processor manufacturers do everything in order to speed this up. So what they do is they have caches, on-chip caches. So instead of writing into memory or reading from main memory, they write and read from the cache. But now every processor has its own cache, right? And it sees memory slightly differently. So there are certain protocols for cache coherency that the processors have to talk to each other and say, hey, I did it right. If you have this in your cache, you better invalidate your cache, and so on. Unfortunately, these protocols are also expensive because they invalidate caches, right? And in most cases, when the programs are executing independent, when the processors are executing independent code and there is no sharing, this synchronization of caches is really unnecessary. So you lose a lot of performance for nothing. So the new approach is to say, let's not make too many guarantees about cache coherency, about propagation between caches. Let's ask the programmer or the compiler to tell the processor when the coherency is necessary, right? Because ultimately it's the program that knows whether it's creating threads and whether these threads are sharing memory, right? So let the programmer deal with this. So in order to deal with this, the processors expose certain new instructions. There are these locked instructions, the lock prefix. There are things called memory fences and so on, and they are used to control consistency, right? From the perspective of languages, though, languages have to provide certain abstractions so that the programmer is not forced to program in assembly language, right? So these things are reflected, let's say, in Java using volatile, in C++ using atomic variables. So when you are accessing atomic variables, the compiler will put correct instructions there, will use the lock or put memory fence and so on. And there are some atomic operations like, atomic increment, which translates into lock increment, and so on. There are fences available, at least in C++, C++11. And on top of these things, higher order languages build things like locks, and so on. So unfortunately, the life of a programmer now is not that easy. It's the programmer has to realize that these things leak into the abstractions that the programmer is using. So it has to deal with these relaxed memory models. So you have to mark your shared variables in a special way, or you have to use locks, and so on. Okay, so sequential consistency, this is a very important notion, and it's not really hard to understand what it is. And in fact, I think we all understand very well intuitively what sequential consistency is, because this is how we reason about programs, concurrent programs. The way we reason about concurrent programs is that when we have two threads executing code, their actions interleave. So it's like one thread is executing a few instructions, then another thread is inserting its instructions, and then goes back to the first thread, and so on. So the interleavings of threads. These interleavings can be different at every execution, depending on, the phases of the moon, or other random events. But you have these interleavings, and what about visibility of actions? Well, if you have a particular interleaving, and look at this picture on the right. So the blue code is one thread and red code is another thread, and they sort of insert their code between the lines. So this is the interleaving. This is a particular interleaving. There can be many more. But in this particular interleaving, if the blue thread modifies stack top, then the red thread will see this modified stack top. Okay, that's our assumption, right? That in this particular interleaving, the write to stack top happened before the read of stack top, even though they are in different threads. So if you want to prove the correctness of your program, okay, and I'm saying this tongue-in-cheek, it's enough that you consider all possible interleavings, and for each interleaving you know which values are read by one thread and written by another thread, or you have more threads than two, same thing. And just consider all of them, and you're done. And why is it tongue-in-cheek? Because of course these interleavings are a multitude. It's an exponential growth of all possible interleavings. But the truth is much worse than that. Okay? Because sequential consistency is broken. Okay? So what happens is modern multicores and modern languages, they don't preserve sequential consistency. They have a different model, much more relaxed. And here's an example of code, sort of pseudocode, that's executed on two cores, core 1 and core 2. And the first thread executes on core 1. And there are two shared variables, x and y, and both of them are 0 in the beginning. So core 1 sets x to 1 and then reads y and stores it into some local variable or register variable r1. Core 2 writes into y and reads the value of x. Okay, so this is sort of, they cross their path. Core 1 writes to x, core 2 writes to y, but they read the opposite variables. So the question is it possible that at the end of the program both R1 and R2 will be 0? I mean, no matter how you interleave these two, one of them will always end up being 1. Right? Because, for instance, if R1 is 0, that means that the write to Y didn't happen yet, right? So in this interleaving, core 2 executes after core 1. But if core 2 executes after core 1, then it will read, when it's time to read X, it will see a 1, because core 1 already set it to 1. So to the big surprise of everybody, This outcome is actually possible. And it's possible on this lowly processor, the x86, the one that runs most of the programs. So when you are programming for the x86, you should know that. And of course, this is completely not in agreement with sequential consistency. It breaks sequential consistency. And if we can't even reason using sequential consistency, that how do we reason about programs at all? And this is where this famous DRF guarantee comes in. DRF means data race free. And the guarantee is that if you have a data race free program, then it will execute like a sequentially consistent program. So first of all, if you look at this code, the fact that you got a non-sequentially consistent answer is because there is a data race. Actually, there are two data races in it, right? Core 1 writes to X, Core 2 reads from X. No synchronization. Core 2 writes to Y, Core 1 reads from Y. No synchronization. So data races galore. This is why this outcome is possible. But if you have a program which has no data races, then you can fall back on sequential consistency and you can reason about your program as you used to. Now, most modern programming languages offer this guarantee. Java offers it as long as you use locks or synchronized and volatile to synchronize your programs, and you don't have any data races, then you can use sequential consistency. In C++, it's also true with exception, and this exception is the so-called weak atomics that I think you should not approach with a 10-foot pole. So, let me summarize. Why is concurrency so tricky? It's because there is this exponential number of interleavings, possible interleavings, when executing the program. It's hard to reason about the program. Even if you have sequential consistency, still you have so many possible paths of execution. So it's really hard to reason about it, and it's also hard to test exhaustively. Because in order to cover all possible interleavings, you would have to run your program for ages. There are so many possible interleavings. And this is why when you have bugs in your program, the concurrency bugs, like races, data races, atomicity violations, or deadlocks, it's very hard to find them. It's very hard to reproduce them. And even if you reproduce them, it's very hard to find the cause. So, how do you test and debug concurrent programs? There are some tools, not many, and they fall more or less into two categories. There are tools that do static analysis, so they actually read your source code, so they require access to complete source code. And because they have to reason about your program, you know, they actually have lots of false positives. That's like the biggest problem with static analysis. Lots of false positives. Because they can only reason about what they know. They know about locks. Maybe they know about volatile or atomic. You know, but if you use anything out of the ordinary, and they don't understand the semantics of your program, right? then they will flag things that are not really bugs. Then there is the second area, dynamic debuggers, and they actually run your program. And they run your program and they try to change the interleavings. They manipulate the interleavings. Some of them do it exhaustively, like let's try all possible interleavings. And of course they can be used only with like extremely short pieces of code, because the number of interleavings is exponential. Some of these programs are more intelligent, some are less intelligent about fixing the finding the possible interleavings that are interesting. They usually slow down the execution pretty drastically. Like some of them will slow it down 100 times. So obviously they cannot be used with anything close to real-time systems. And they offer poor coverage, obviously, because what the meaning of coverage in concurrency is not really useful, right? I mean, full coverage would mean you have to run through all possible interleavings, and this is just could be longer than the age of the universe. So our company, Concurrency, makes a debugger, or a program that can be used to test concurrency bugs, called Jinx, and it falls into the category of dynamic debuggers, and it tries to counter all these problems that come with dynamic debugging with intelligent heuristics and technologies. So for instance, the slowdown is manageable with Jinx. It's of the order of 2 times slowdown, because it does analysis at random intervals. So it picks an interval, does its analysis, the interleavings, and then continues running the program at full speed, and then does another sampling, and so on. And also it picks the interesting subset of all executions, because at every interval that it does the testing, it analyzes the execution looking for communications between threads, and it only changes the interleavings that are important for communications. So it's trying to force data races, and understands the idea what data race is, and will try to force it, or force atomicity violation. So this is all, and normally at a webinar I would ask you to ask me questions, but since I'm recording this, you'll have to maybe write comments or send me email. There are many more resources at our website, and in particular the blog.concurrency.com. This is a blog that contains a lot of interesting information. It's not really, a marketing blog. I'm trying to keep marketing people away from it, so that real content is available there. Discussions about memory models, about multi-threading, and so on. Interesting things, really interesting things. Okay. And if you want to learn more about our product, Jinx, if you really need to debug your concurrent program. If not all your concurrent programs are always correct, then please look at our website, concurrency.com. Thank you very much.